Welcome back, everybody, to the latest Collision Hub webinar with our friends again from Miller Electric today. Ace is back with us along with Joe, and we're going to be talking about GMAW basics for aluminum welding. So a lot of vehicles switching to aluminum or mixed material vehicles. So not exactly sure where the future of aluminum welding is going to go versus other attachment methods, but certainly is a prevalent repair procedure today for a lot of aluminum vehicles. Ford allows it for all the F-150 repairs, so pretty large volume vehicle there, obviously. So without further ado, I'm going to hand it over to these guys. Let them take after it. We're on the webinar again today, so if you have any questions, please feel free to use the chat feature, the Q&A feature, or raise your hand, and I'll keep an eye on that, and we'll try to get you in and get your questions in there. All right, so with that, it's all yours, guys. Take it away.
Yeah, thanks.
Great, thank you, Jason. Yeah, like Jason was saying, today we're going to be talking about GMAW basics for aluminum. This is a hot topic, and I'm excited to talk about it. So today, I just want to touch on safety first. We're going to be then talking about GMAW aluminum. Going to be talking about the process, types of transfer, machine setup, some applications, and also I want to get into some common issues seen with aluminum and some things to remember. So hopefully it'll help you guys out in your shops and prevent some issues. So first off, just talking about safety, always protect yourself. I like to just always reiterate that. Make sure you're wearing a proper welding helmet, proper gloves and jacket and safety glasses. You want to protect your skin because that welding arc is very bright. And then also be aware of your surroundings. Make sure that you're always welding in a safe environment and that you're protecting those that are around you. You want to, if you're welding, that arc light is going to be bright. You want to warn your coworkers that you are going to be welding. All right, so GMAW aluminum. So if you've been able to listen to the other webinars, GMAW aluminum, it's a gas metal arc welding process. Basically, we're just welding on aluminum. We're still using a constant voltage power source with either an internal or external wire feeder, and the wire is continually fed through from the machine through a MIG gun, and then once the wire makes contact, it initiates an arc, and that molten aluminum is carried across that arc. So talking a little bit about transfers. So we've talked a little bit in the past about multiple transfers like short circuit, a little bit on globular. We've also talked about spray and pulse spray. When we're welding with aluminum, there's two main ones that we're going to be focusing on. I kind of want to touch on spray transfer just because it's the original, the history is there, but with spray transfer, you have a steady stream of droplets that transfer across the arc. But one of the issues with that is it can be restricted to flat and horizontal welding positions. Also, it puts a lot of heat into the plate. When we're talking about, pulse spray transfer, basically we're ramping up and down our current or our amperage, and with each pulse, a droplet is going to be transferred across the arc. This allows welding in any position. So a continuation of that, spray transfer is typically very hot. It's generally used on thick plate, and it requires high voltages. With pulse spray, it has a wide range of use. We can be welding on very thin aluminum. It can be 18 gauge, 20 gauge. We could be welding up to half-inch thick aluminum. So it's got a wide usability, wide range of use. Also, you'll see that when you're running GMAW aluminum, you'll use a variety of diameters of wire. Really common ones are going to be 035 or 047. Sometimes 047 is referred to as 3/64. So one process that you'll see not used very often with aluminum is short circuit transfer. And I just want to lightly touch on this. I did a little sample weld this morning just to show what can happen when you're running short circuit. On aluminum, it can be very difficult to control your heat. So looking at that picture over on the right, you can see right at that start, it's very cold and it roped up right on top of the plate. Didn't wash out at all. There's probably no penetration into the plate. And then the other thing is not too far into the weld, you can see that it does start to wash out and it looks pretty nice. But because it's so difficult to control that heat in aluminum, if we were to keep going down that plate with that weld, it'd probably burn through in another inch or so. So next I kind of want to shift a little bit and talk about parameters used and how they vary between spray and pulse spray. So when we're set up for pulse spray, when we're set up for spray, we're going to be adjusting mainly our voltage and our wire feed speed. What our voltage will do, it's going to adjust our bead profile, and it's also going to affect the arc length. Arc length being the distance between the end of the wire and the molten puddle. Our wire feed speed is going to adjust the amount of metal that's going to be deposited, and it will also affect our penetration. Now it kind of shifts gears when we jump over to pulse spray, because our main two adjustments that we're going to look at is arc length, or arc adjust is another common term for it. And then we're also going to be using wire feed speed. So with our arc length, we're going to be talking specifically between the end of the wire and the molten puddle. We can adjust how big that distance is. So the adjustment varies our voltage is what it actually affects, which with a longer arc length, it'll increase that voltage. With a lower arc length, it's going to lower the voltage. And it'll tighten up. I got a couple of videos that we're going to look at here in a second. For wire feed speed, that's going to adjust our overall heat input. Also, when we're running pulse, it's going to be synergic. And what that means is after we've dialed in that arc length to what we want it to be, and we start adjusting our wire feed speed, it's going to maintain that arc length no matter what wire feed speed we use. So it'll transition smoothly. With when we are adjusting our wire feed speed, though, it is also going to adjust a number of other parameters, which we're going to get into in just a minute. So kind of diving deeper a little bit into a pulse waveform, I like to look at this because it kind of shows kind of what is happening in the background. But we have a number of variables here that when we are pulsing, we're going between a low current or amperage, and then we're ramping up to a peak. At our peak, this is when we're going to transfer a droplet. Then we'll ramp back to our background, and that background is going to help keep our arc lit. It's going to help keep our puddle fluid, and then the process will cycle through. It'll keep happening. Sometimes you can be down to 27 pulses per second, depending on where you're at with wire feed speed. Sometimes when you're on the higher end, you might be up at 200 to 250 pulses per second. So that pulse per second, that frequency, the amount of droplets that we're transferring will vary with wire feed speed. And then I really like this slide because it kind of demonstrates just a little bit more information as to what we're going to see when we start changing some of those variables. What's really nice is the machine's being synergic. When you're running pulse, you don't have to worry necessarily about all these variables, but it's good to have an understanding of what is going on. So looking here, as we increase our pulses per second, one of the things it's going to do is it's going to increase that arc length from the end of the wire to the puddle, and it's also going to increase our average amperage and also increase the heat input. So when we're welding on really thin aluminum, some of these auto body panels or some of these automotive parts might be down around 18, 20 gauge thick aluminum, and it's very thin. You have to be very cautious of heat input. And so one of the things that you'll notice is when you get down on that lower end and you're using a low or a slow wire feed speed, you're looking to transition or transfer fewer droplets, you're going to see fewer pulses per second. And when we get into the video that's coming up, you can actually hear that. So I wanted to put together a couple videos. This one's a little bit fuzzy, but it kind of shows that as we're welding, we're going to start out at a low wire feed speed and just watch that puddle and the arc. It's going to widen and increase as we increase that wire feed speed. So maintains the arc, but as I'm increasing that wire feed speed, that puddle is getting more fluid, it's getting hotter. You can start to see now we're starting to penetrate more into the plate. So that's one adjustment. So synergically, it's going to adjust. Now let's look at our other adjustment for pulse. Let's look at adjusting our arc length. So I got two videos here. The first one's just going to be like a pretty tight arc length, and then basically with the adjustment on the front of the machine, I increased it for the second video. So let's watch the difference there. So you can see pretty tight, which depending on the joint that you're going to be welding, you may want to adjust that so it's to your benefit. Now you can see that arc length lengthened, longer distance from the end of the wire to the puddle itself. Here I have some zoomed in slow motion video to see the end of the wire. So this first one, we're going to have a tighter arc length. So you can see that overall distance is not very far between the end of the wire and that puddle. And then as we increase that arc length, you can see it's going to transfer that droplet farther across the arc. So if you're swapping between joint types, if you're doing like a butt joint, you might see yourself increasing your arc length a little bit. If you're doing a corner joint or a T-joint, you might see that you're tightening that a little bit to control that arc, to control the puddle flow. But I really like this because it kind of shows you a little visual what's happening at the end of the wire. So now I kind of want to shift gears and talk a little bit about machine setup. What's typical? What are you going to see out there? If you're new to aluminum, what should you expect, or what's common in industry? First thing I want to talk about is wire type. It's going to be divided into basically two series of wire. You're going to have 4,000 series of wire is most common, or 5,000 series of wire, and we're going to get a little bit more into that in just a second. Wire diameters: 1.2 millimeter, 3/64, 035. It's all dependent on the repair spec, really, and what the auto manufacturer is calling out that they require for that repair. So I'd highly recommend for your setup for MIG aluminum that you check with that manufacturer first. Shielding gas: whenever you're welding aluminum, typically you'll use 100% argon. And then drive rolls, this is critical. So the type of groove is a U-groove. What that does is it allows that wire not to be crushed, because if you have a V-groove, it's going to put a pinch on that wire and it's going to misshape the wire, and then you might see some arc performance issues. And then when it comes to contact tips for setting up for GMAW aluminum, typically when you go to grab a contact tip, there's typically one size on it. So you might see 035 contact tip, you might think, oh, well, that works for aluminum, it works for steel, it works for stainless steel, everything. But actually what you need to look at is there are specific contact tips for aluminum. And typically they're oversized just a little bit, because as that wire is going to heat up, it's going to fluctuate in size and diameter just a little bit. So like, for example, at the end there, I'm talking about, so you might have an 035 size contact tip for aluminum, and it might also be for steel, but it'll say for 040 diameter steel. Something to keep in mind. How are we doing on questions? Do we have any questions so far?
We got nothing coming in. You're good.
All right. Next thing I wanted to touch on was guns and where they have benefit and where to use them. So for welding aluminum, you can use a regular MIG gun, but what you want to make sure that you use typically a 10-foot gun. Typically, if you're going to run a regular MIG gun, you're only going to be wanting to run 047 or 3/64 wire, that bigger wire diameter for aluminum, because the wire is so soft. If you go any smaller with diameter, you might see some bird nesting. So with that 047, usually it's stiff enough that you can run it through a 10-foot gun, but it's critical that you have the appropriate liner for that, which is Teflon. But this makes a great setup for a shop running that 10-foot gun, because typically you can be right next to your car that you're going to be welding on, and you won't need the additional motor to push that aluminum. So moving on to a spool gun. So a spool gun allows you to, it actually has a motor built up in the spool gun itself. You're going to be able to load a small spool of wire and feed that through. It's going to give you a little bit different capability. You're going to be able to use smaller spools, and you'll also be able to get farther away from your power source if needed. So sometimes spool guns will allow you to get 20 to 25 feet away from the welder itself. And then the third gun there that I wanted to talk about was push-pull gun. It's really common, but typically it's mostly seen in heavy aluminum welding because you can run a large spool back in the machine. It allows you to get 30 to 50 feet away from your welding power source. Typically not really needed in an auto collision repair shop. So typically one of these two guns should be able to work for you. Joe, did you have anything you wanted to add with that?
Yeah, just the difference between them, the big difference there is with the spool gun, everyone was kind of accustomed to that, and we had those in the Ford program with a previous model and so forth, and with technology and so forth, we were able to just use a standard MIG gun, which makes it so much easier to work with. Sometimes some of the spots you have to get into, what have you, the spool gun or the push-pull might be a little clumsy. Not that they don't work effectively, but again, it's about comfort, convenience, and making sure that you're getting a good quality weld. So, switching everything over to a conventional MIG gun just makes more sense. It's just a little easier to handle and work with,
Absolutely. Thank you. So next, I kind of wanted to shift gears a little bit, just real lightly touch on some base metal types you might see out there. There's all different kinds of aluminum, but they're basically split up into series. So 1000 series aluminum, you're going to see it's pure. It's typically used with chemical tanks, and it's known for its formability. 2000 is going to be high strength ratio. It's mostly seen in aerospace. 3000 series is known for its formability, high temp service. 5000 series for its formability. You're going to see it a lot in auto trailers, and it's really known for its strength and toughness. And then 6000 is very, very common. It's going to be high strength and toughness, and you'll see it a lot in automotive and trim and truck and trailer applications. So now I wanted to talk a little bit more about wire types. So that 4000 series versus 5000 series. So a really common one out there is going to be 4043. And 4000 series wire, when you're setting up your welder and you're running pulse, it's gonna ask you, do you want to run 4000 series or 5000 series? Because those two kinds of wire will run a little bit different dependent on the machine that you're welding with. And so that pulse program will be dialed in specifically for that wire. And so typically if it's a 4000 series wire, you can just select a 4000 series program, and it'll typically run most wires like that fairly well. So one 4000 series wire that you might see is one that Tesla spec'd. It's the 4145. It's known for its moderate strength, its low melting temperature, low smut, and discoloration. And then also what's really important is it has low hot cracking sensitivity. And what you're really going to see with that one is you'll see pretty shiny welds. You won't see very much black around the welds, as opposed to like a 5000 series wire. It's really strong. Um, you're going to see 53, 56 is used a lot on aluminum truck frames, but one that's really common out there is 55, 54, which is spec'd by Fords for the F-150, Ford for the F-150s. It's moderate high strength. It has really good feedability because it's a harder wire than a 4000 series. One of the things you'll notice that when you are using it in your welder, it feeds a little bit easier than that 4000 series. One thing that you might see with that, and we'll look at that in a minute, but you'll see a little bit of black around the welds usually, which is magnesium oxide that just flows around the weld a little bit because of the arc. So real quick, a lot of people don't know about filler metal charts and how to find those, but every manufacturer is going to have a filler metal chart that basically it'll show you, have you look at your base metal, so what type of aluminum you're welding to what type of aluminum. And what's really cool about this is using a chart like this, if you're curious what kind of aluminum wire should I use, you can either reference this, but I recommend first look at the vehicle manufacturer and what they specify you have to use for repair of that vehicle. But if you're doing something else like outside of automotive and you're curious, what filler wire can I use for this application, this is always a good starting point. So just want to make sure everybody knows that that's out there. All right, so now I kind of want to shift gears a little bit, we're going to talk about a variety of different things, but basically it's things that I've talked with lots of people out in industry about, issues that they've ran into, and troubleshooting techniques for little things you can do in your shop for your collision repair business to eliminate any issues. First, this is critical. Wire storage is so important. Basically, what you really want to do is store any wire that you have in a dry location. What I always recommend to people is cover it up, put a plastic bag on it, because if you're doing any kind of body filler, if you're prepping a car for paint, if you're grinding off an old weld, that dust is going to go in the air. It's going to get on that wire, and as soon as you start welding with it, it could contaminate your weld. One of the other things is you want to designate your welder for aluminum when you're set up for it. If you're welding with aluminum, you really want to make sure that you're using the right setup. If you have an aluminum gun, you want to use that gun for only aluminum. Don't be running steel wire through it and switching back and forth between aluminum and steel, because one of the issues there is as that wire goes through that machine, if you're using the same liner, it's going to pick up some of that steel and it's going to put it into your weld, and you'll see some issues there. Might have issues like porosity. You'll definitely see some issues with arc performance, and it just is not good. So that's one of the things that I highly recommend, that designate your welder for the process that you're going to be using it for. Another point I wanted to talk about was metal prep or metal preparation. So can't say this enough with aluminum. Aluminum is very, very picky on how clean it is. The quality of the weld is dependent upon the quality of the metal preparation. So I got a couple pictures here, and the top one is the T-joint before it was welded. Basically, it's really dirty. There's a whole bunch of gunk on here. I just wanted to show an example of what would happen if you didn't prep that material. So I went ahead and welded it, and then I broke that weld to look on the inside. The weld actually looked okay from the visual appearance up above, but once you broke it open, you have all these little spots. You see these circles of porosity. So you want to eliminate any porosity that you can, because that's going to cause a defect in your weld. So I got some steps that I like to do to make sure that you get that metal as clean as possible. First, you want to make sure that you remove any paint at least a couple inches away from the weld joint. And that's not only on the front side of the joint, but the back side as well. because there is, whether it be a primer or paint on the backside, it can get drawn into the weld. Once you get that off of there, what you would like to do is, what you'd want to do next is degrease all your weld surfaces. Typically, a lot of welders out there use acetone because it works really well to get everything off of there and it doesn't leave much behind. You want to make sure you use like a clean paper towel or a cheesecloth. And one thing that I've seen guys do in the past is they'll grab a air compressor and they just blow off the material and they wipe it down. But one of your issues there is you could have just introduced oil from the compressor or any water from the compressor onto that weld surface. And now you're going to go weld it and it's going to draw that into the weld joint itself. And you could have more issues like porosity or a weld fail. So after you've cleaned it off with a paper towel or a cheesecloth, usually what I'll recommend is hit it with a stainless steel wire brush. What's really critical is you make sure that that stainless steel wire brush is designated only for aluminum use. If you go use it on steel, then back on aluminum, you'll draw those contaminants into that aluminum. So make sure that that's designated for aluminum use only. And then after you're done with that, wipe it with acetone one more time. Another common issue that I see out there is just ensuring that you have the right right drive roll set up. So on this one, I have 023 V groove in there just to show you that it is incorrect. You would want to use a U groove for aluminum. But also, this tension here is crucial. If you have that tightened way too tight, it's going to put a lot of pressure on your drive rolls, which will put a lot of pressure on your wire and could crush the wire. So something to pay attention there. You might want to loosen up that tension just a little bit for aluminum. Next thing I would like to talk about is, we've talked about this in the past few webinars, but where this really comes into play is you always want to make sure that you're using the right technique with aluminum. Typically, you'll always want to use a push technique because as you're welding with aluminum, you really want to make sure that you get that shielding gas out in front of the weld. So if we were with the diagram here, if you're moving from left to right, you'd want to make sure that your wire is pointed in the direction that you're going. It'll help that shielding gas get out in front of the puddle and protect it from any contaminants in the air. And then also the same applies for your work angle here. So the molten metal puddle will flow wherever you point it to. So just to kind of wrap up, I hope my goal here today was to touch base on the GMAW aluminum process, how to weld it, a few techniques on how to make sure that you don't get contaminants in your weld, make sure you're clean, clean, clean. And yeah, I'll turn the time over if anybody has any questions that I can answer.
All right, thanks, Ace. We don't have any questions coming in. Sure, nobody's got something out there for me, for us, for Ace. Lost my mouse here.
Come on, don't be shy.
Yeah, this is like the perfect time to ask any questions that you have.
Yeah. Ace, what are some of the problems I can run into if I'm using, I guess I call it an incompatible electrode wire with the type of aluminum I'm welding? What kind of issues am I going to run into most often?
So one thing that you'll notice right off the bat is, when you go to start the welding arc, it's really dialed in for that diameter of wire usually and that type of wire. So if you're using something that's different from what it's dialed in for, you might see that you might get a flare in the start, so your arc might go long back to the contact tip. You might see a cold start. And then also one of the things that you're going to see is when you actually get into the weld, that transfer might not be transferring the right size of droplet, or might not be transferring like it should with the actual wire it was designed for.
Okay. Now we do have a question coming in now. It's a great question. How does oxidation have an effect on the welding?
Oh, that's a really good question. So that's one of the big problems is, so with aluminum, you're really trying to get that oxide layer off of that outer piece, or I guess outer shell. So that's where material prep really comes into play and really helps out. So one of the things that will really help out with that oxidation, getting that off, is using that stainless steel wire brush. Making sure that when you use that, it'll help break that oxide layer, and then it's going to help you be able to get a smoother weld and get adequate penetration.
Okay. So I've got another question here, which is another good question. And if like, Ace, this isn't your area of expertise, I've got some background in this based on some research I had done previously. So Bill is asking, is grinding of the weld afterwards a safety concern for possible explosion of the aluminum dust in a body shop situation?
Explosion of aluminum dust? Yeah. If you wanna take that, Jason.
No problem. Yeah. So this is why when I was at ICAR, we done a lot of research with the Aluminum Association in collaboration with some other organizations. And what we found, so certainly aluminum dust in the right, with an ignition source, airborne, the right concentration, the right size particles, absolutely will explode, as will powdered sugar, grain, etc. Correct? What we found was that the aluminum size, the particles that when we grind, especially when we grind, if we sand it even with 80 grit, not an issue, but certainly if we're using something more aggressive, those particles aren't going to be suspended in the air. They will fall to the ground. The recommendation typically is to use a vacuum cleaner for aluminum dust. But we did a lot of research on it, and we had to generate a fairly significant amount of aluminum dust just for the testing. And we sanded for hours and hours and hours just to get enough dust to even test on it. The other thing, when you're talking about grinding or sanding on aluminum parts and panels, the bulk of what you're sanding is going to be, clear coat and base coat, primers, etc. There's not actually that much aluminum dust in the mixture itself. Now, again, if you make a weld and then grind that down, that's going to be mostly aluminum. But I guess to kind of answer your question, Bill, there really isn't that big of a concern to the point where the whole aluminum curtain debate and the galvanic corrosion, I can go on for a long time about all this. I'll try not to do that today, but not to say that good hygiene isn't important, not to say that safety isn't important, but some of those things may be a bit overstated, and maybe we may be a bit more concerned than we need to be with some of that. So to kind of answer your question, Bill, no, it's not that big of a concern. But again, not to say don't be safe and don't use good hygiene. We certainly want to promote that, but it's not that as big of a concern as we once thought it might be. Another question: Do you dress plug welds the same as if it were steel? Is another question that's coming in here. So again, if you've got an exposed area, yeah, we're gonna want to grind those down a little bit, sand those down a little bit. But to answer that question, Mike. What else we got for questions? Joe, you got anything to add or questions that you've got for Ace here?
Oh, kind of. Just to reiterate, I can't emphasize the importance of the contamination issue with the wire and so forth. It's something that I think typically in some shops it's like they finish up with the welder and they go and park it in the corner, and where you're not using aluminum on a day-to-day basis like you might a MIG steel or maybe even a silicon bronze. What happens is it gets parked in the corner and you don't use it again for a couple of months, depending on that time of year. You don't want to have issues and go to jump back on that job and have the thing just stall because the wire is contaminated, you're not getting a good arc with it and so forth. And this has come to me through some other groups and other people that are in the welding industry that it was a joke, said, yeah, every 3 months you got to run back out and give them another roll of wire because they just let the aluminum get contaminated over there. So that's something that I think all of us would agree is good hygiene and good safety practices with that. And, throw in a Ziploc bag or Tupperware bowl or something like that and keep everything contamination free. It's only going to improve your efficiency down the road.
Yeah, no doubt about that. When we were doing a lot of the Jaguar aluminum training, again at my former role, those guys were obsessive about making sure that wire was stored. Getting them out of the machines every week and making sure, and they were welding every day, right? And they were definitely concerned with that, and there's definitely some issues with that. Ace, can you tell us a little bit maybe more about cold starts and craters. I know those are a couple of concerns that we have typically when we're welding aluminum. Can you just expand a little bit more on that for us about some prevention tips and what we can do to adjust for that?
Yeah, so typically an issue with aluminum is getting that arc really started, getting it hot right away. So kind of for those who don't know what a cold start is, it's basically you don't have enough heat right at the beginning of your weld, so you don't get the penetration that you need. And so there are machines out there that have it built in where it's either pre-built in with a hot start or you can adjust that yourself. So that may be an adjustment on top of, whether it be arc length or wire feed speed that you can control to eliminate some of those cold starts in that cold plate. So one of the other things that you want to look out for, and maybe let's see if we got a picture of it. But when we're talking about the crater, we're talking about right at the end of the weld.
Yep.
And sometimes what can happen is if you don't have adequate rebuild up at the end of the weld, then you can run into an issue of the wire. Oh, here we go. So right here at the end of the weld, we have our crater.
I stopped your screen sharing, Ace.
Sorry about that. No problem. So right at the end of the weld, you're typically always going to have a crater. What you want to make sure of is that your crater isn't too large, or that your crater has sufficient fill in it, and that's an adjustment on most machines that you can add at the end there. So after you let go of the trigger, it's going to basically add a little bit extra wire at a little bit colder setting so that it'll fill up that crater and prevents any crater cracking. So.
And then another option to prevent both those would be to tail in and tail out, correct?
Right.
Is that going to be more of a preference as far as using the machine settings versus tailing in and tailing out, or is there a typical best practice for it?
It's going to be mostly machine settings. I think every application is going to be a little bit different. So it really comes down to what you would like as the person welding.
Okay. All right. Any other questions? This is our last scheduled one with Miller Electric right now. So fire away. Even if you've got something that maybe is not specific to aluminum, if you've got specific to MIG brazing or steel, like we had talked about previously, or even maybe an equipment question about, one of the pieces of equipment that are out there from Miller. If anybody's got any questions, now is definitely the time to ask. We got a couple experts here. Pretty quiet out there today. It's Wednesday. It's like a Monday or something, I guess. But
Yeah.
I'll probably have a few questions next week for you guys when I'm
no, I'm sure
at 2:55 fired up on Monday morning. We'll see.
You all set with that the answers from Chris the other day?
Yeah, I think I'll definitely check that. Like I said, I looked at the one I had here, Joe, and I'm 99% sure there was no writing on the other side of that 035 one, which that was my natural assumption too, was it's going to be on the backside, and I looked and it's not.
Yeah.
What I'll take a closer look. There are definitely two grooves on there, so I'll take a closer look at it. Maybe there's
some of the smaller units have the double-sided with the 255 that you have. It does not, and somehow I ended up with some extra ones here. So as soon as I got your email, I said, "So let me check." It costs it's what you already have, but Chris had a satisfactory answer. So if not, we'll just blame it on him.
There you go. Hey, we do have another question coming in. Ace, you got to explain. When we're saying tailing in and tailing out, what exactly are we doing?
So essentially what we're talking about there is you're adding that. It kind of ties to cratering or adding a hot start. So tailing in, you're easing into that weld, so you're not quite there with all the energy or all the power. And then at the end of the weld, when we're going to finish up the weld, you're trying to fill that crater. So essentially it's the same. It's very, very commonly talked about with AC TIG as well, because you're trying to limit the amount of heat at the end of the weld. So as that aluminum is solidifying, if it cools off too quickly, it's going to pull apart, and that's what causes your crater cracking. So when we're talking about tailing out, you're just trying to limit the amount of heat input at the end of the weld.
So we're starting off the joint to ramp that up a little bit. So we're starting off the joint and then tailing into the joint, making our weld, and then tailing out of the joint to let that ramp down. Okay. Hopefully that's a good explanation for our question asker here. So, anything else from anybody? All right. Well, if not, if something comes up afterwards, certainly can email me, Jason at collisionhub.com, and I'll pass the questions on to Ace and Joe to get those answered for you. I do want to again thank both you gentlemen for taking time out of your day to share some of your expert insight with the group. It's certainly been a pleasure, and really appreciate Miller Electric support, and look forward to continuing to work with Miller Electric here in the future, and getting some more collision repairs with some blue equipment in their shop.
There you go. Well, I appreciate everything you guys have done, Collision Hub, and you guys do a great job. Keep up the great work. Thank you for having us.
Thank you very much.
Thanks,
Appreciate
everybody. Thank you, Jason. Appreciate it.
All right, everybody have a great day, and
All right, take care.
we'll see you next week. Bye-bye.
See ya.
Take care. Thank you.